All right, we start?
Yeah.
Okay.
All right. You go.
Thanks for coming to the second lecture.
Yeah.
Today we will try to have a break in the middle and regenerating.
Yeah, regeneration and question asking occasion. Okay, so this is the last slide we had yesterday. Basically, we've used angle action coordinates to understand the quasi-periodicity of orbits in interesting potentials. And we have taken on board that the significance of the existence of angle action coordinates is that orbital surfaces, in phase space, orbits are confined to tori. In four-dimensional phase space, they're confined to two tori, so donuts. In six-dimensional phase space, they're confined to three tori, which are analogous to a cube with opposite sides identified. Okay, so onwards. And so what we would like to have, what we want is an apparatus which computes these tori for us. And in an incredibly limited range of potentials, we can do that via the Hamilton-Jacobi equation, which, as some of you will know, is a classical limit of the time-independent Schrödinger equation. So what we're going to look for is the generating function S, depending on a newfangled momentum, J, and an old coordinate X, ordinary boring spatial coordinate, for the canonical transformation that takes us from X and P, ordinary coordinates, to the coordinates, angle action coordinates, which make dynamics trivial. And of course, given this generating function, the old-fashioned momentum will be ds by dx, and the newfangled coordinate will be ds by dj. That's how canonical transformations work. We know that the Hamiltonian, the x's and p's, which lie on the torus, in other words, the position and momenta of points on the orbit, satisfy h of px is equal to E, the energy. So if we replace P with ds by dx, then this becomes a partial differential equation for the generating function S. Now, unfortunately, this is not a linear, unlike the Schrödinger equation from which it derives, this is not a linear equation because this thing typically is going to be p squared over 2m, and so we're going to have ds by dx squared over 2m appearing in it rather than what we would like, rather than a linear thing. So the range of potentials Hamiltonians which we can solve this equation is incredibly limited. In practice, you can solve it in coordinate systems for which the Hamilton-Jacobi equation separates. And then what you find is that the actions are functions of the constants of separation. There will be if we do this in four space-based dimensions, there will be only one separation constant. If we do it in six space-based dimensions, there will be two separation constants. So we will have one or two separation constants, and the energy as this number here, E, will be another constant of the motion. So we will, and S, the solution to this equation is going to be a function of the separation constants C and X. So in the separation constants, I'm including E. Sorry, in the constant in C, I'm including E and however many of these separation constants we have, right? So we're going to have some function. The solution to this equation is going to have some function of X with parameters, the C's, and it's going to be and from that, by differentiating this with respect to X, we will get P. So what we're going to do is get P as a function of X, and then we're going to be able to do an integral dx, P is a function of X. Now in practice, because H is P squared over 2m, this is going to say something like ds by dx squared is equal to E. And when we solve for ds by dx, aka P, we're going to have a plus or minus. So this integral we're going to be able to do as x increases, we're going to be able to do it using the plus square root part for P. And then eventually at some x, P will go to naught, and then we'll switch to the negative root, to the minus square root version of P, and start decreasing x. And so we're going to have dx is negative, P is negative, and so we will get more values. And in this way, we will do a complete cycle. We'll take x from a minimum value to a maximum value, and back from maximum value to minimum value, getting a non-trivial integral, because in the meanwhile, p will have changed sign. And we know from Poincaré's theorem that this integral p dx around any path in phase space is independent of what canonical coordinates you use. So I'm going to do this, say I'm going to do r dpr, for example, up and down. That could be written as j dot d theta, where in principle there'll be a sum here over the jr and j phi and stuff. But the point is that only, and the j's of course are constants, so they could be taken out. So we can write this as j dot d theta, and only one of the thetas in this process is going to increment by 2 pi. All of the thetas typically will change, but only one of but all but one will go back to their original value. And so these integrals d theta, the vector you get by integrating d thetas will be something, nothing, 2 pi, nothing. So we will be able to say that this integral that we can work out is equal to j, whatever had whichever j it was that had the non-vanishing integral.
Ignore me. I just heard the noise and
just some machine is unhappy. Right. Okay. So so basically, right. What I'm explaining is how out of the solution to the Hamilton-Jacobi equation, which depends on these rather arbitrary constants, we're going to extract the magic numbers, the actions, which are the correct way to characterize the toruses. Yeah. Right, onwards. So that's how we use the Hamilton-Jacobi equation. You can solve the Hamilton-Jacobi equation. It's sort of standard exercise in mechanics courses for the simple harmonic oscillator. Even that is actually, turns out to be quite a complicated round. It's not completely trivial. Even the harmonic oscillator, and the Kepler potential is extremely not trivial. And you can't do it. You can't do the necessary integrals analytically. I think in only one other, which I'm going to talk about. So the most general coordinate system, as far as I know, in which you can do this, is our confocal ellipsoidal coordinates. The way you can think about this is you start from ordinary spherical coordinates, where you've got you have spheres, spherical shells, which you label with r. You have cones with an opening angle around the z-axis theta, which you label with theta, and you have planes phi equals constant, which have a spine which join on the z-axis, right? And when you go to confocal ellipsoidal coordinates, you turn the spheres into ellipsoids, which are traditionally labeled with lambda. You turn these cones into hyperboloids, which you label conventionally by mu, and you have these planes become other hyperboloids, which are perpendicular to these, which you label with nu. It's a ghastly coordinate system, the confocal ellipsoidal coordinates, but it does allow you to solve the Hamilton-Jacobi equation. And I think Steckel in the late 19th century showed that that's the most general system in which it can be solved. Right, and the 3D harmonic oscillator and the Kepler potential are appropriate limits of this system. This system, of course, depends on where you put the foci. You've got two focuses that you can put someplace or another. So you've got two free parameters in defining this coordinate system, and if you use those appropriately, you can include the Kepler potential and you can include the harmonic oscillator. So we're going to use extensively just an axisymmetric version of this, where basically you employ the ellipsoids and these hyperboloids, but you leave the planes phi equals constant. You leave them alone. So this is what the coordinate system is going to look like. This is now in cylindrical polar coordinates. These are surfaces of constant lambda. You can see they're ellipsoids. You can see they're confocal. The foci lie here and here somewhere. And these are the surfaces of constant mu, which I hope you can imagine are distortions of cones, right? Because this is, yeah. So these in the spherical limit, these become surfaces of constant theta, just cones. And I'm going to use a much more convenient notation is to label these things by a parameter called u, and these things by a parameter called v, because then with hyperbolic posh and shine, you can write the formula in this axisymmetric case in a nice simple way. So, and we're going to specialize on the isochrone potential. Here is the isochrone potential, which was dreamt up by Michel Hénon, 1960 something. And he was attracted to this potential because it is the potential in which the radial frequency, the frequency of radial oscillations, depends only on the energy, not on the angular momentum of the orbit. So low eccentricity and high eccentricity orbits at the common energy all have the same frequency. There are reasons why he thought that was interesting. I think it probably isn't very interesting, but this potential is a lovely potential because it has two parameters, obviously this trivial scaling m, but more interestingly, it has this parameter b, which determines something like a core radius to the mass distribution that generates this thing. So it's a two-parameter potential, and the remarkable, it's not particularly remarkable that you can solve the Hamilton-Jacobi equation for this, but what is remarkable is that all of the functions you need, the transformation from theta and j to r and p, etc., are completely analytic. You don't have any integrals you have to do numerically. It's all completely analytic. And once again, the 3D harmonic oscillator, the degenerate harmonic oscillator, because this is a spherical potential, whereas the general Stekel potential is not spherical, but this one is spherical. And so the 3D harmonic oscillator, the degenerate one, is a limiting case, and the Kepler potential is again a limiting case. Right. So now the torus mapping scheme. So what we've got is from the Hamilton-Jacobi equation, we have got some models. We've got some model tori. We've got some examples. Exhibit A, we have got examples of toruses, orbital toruses. And what we want to do now is to map those onto a general potential using a canonical transformation in such a way that when they arrive, they sit on surfaces of constant, they're within surfaces of constant Hamiltonian in the new phase space. So obviously they start off as being in surfaces of constant isochrone potential, isochrone Hamiltonian. And when they arrive, I want to make sure that they're on surfaces of constant whatever Hamiltonian I was given, the galaxy's real Hamiltonian, whatever. And how do we do this? Well, the simple basic version is we write down a generating function to take us from what I'm going to call the toy angle action variables, theta toy and j toy. Where's j toy gone? It's not here yet. It's coming from derivatives. Okay, so the T stands for toy, and we're going to have the toy angle action variables, which are the angle action variables of the isochrones, which are good because we have these analytic formulae for converting them into x and v. And the other thing that's appearing is j of the true. These are going to be the action variables of the galaxy's Hamiltonian, or whatever Hamiltonian I've been given. So this is the form of the generating function. This part generates the identity transformation because the theta that belongs to j is ds by dj, and you do ds by dj on this and you get theta t. So if I got rid of all the s, these are numbers these are the numbers we're going to search for, sk of j. So if this wasn't there and the generating function was just this, we would have an identity transformation because we'd have the theta was equal to theta t, and jt, which is equal to the derivative of this with respect to theta t, would be just j. So this part is the identity, and this part is shifting us away from the identity. And in principle, I mean, when you program this on your computer, you don't have all these complex numbers because symmetry will in practical cases make it possible to write this as just in terms of signs, so everything's real. But when you're doing the abstract work, it's often more convenient just to leave it with exponentials. So what do we do now? We fix J. We say to ourselves, I would like to generate the torus associated with orbit, the torus with actions J in my galaxy potential. So we fix on J, we specify it. And then on the nodes of a grid in theta toy, you compute J toy just by doing the differential of this, right? J toy is the derivative of this, so J toy is equal to J plus you take the derivative of this with respect to theta toy, which brings down various k's and stuff. You can do the derivation. So from this, I can express J toy as a function of in terms of J, and these numbers and a Fourier series, the sum of these numbers at given whatever it is. And I know what J is because I chose it. I make some guesses to what the S's are. Probably noughts in the first instance, and then that enables me. So then I know theta t and jt. Knowing theta t and jt, I can compute x and p, right? And then because I've got x and p, I can compute the galaxy's Hamiltonian, h of xp. And all I do is tell the computer to adjust the sk to minimize the variance in H, because if H is constant over the image torus, which is what we're generating points in the XP in the image torus. If H is constant at those points, and therefore the variance of H vanishes, then that is an orbital torus. It turns out that's all you have to do. Okay, now that is almost all you need to know. But there is a slight complication that you can see that this procedure isn't going to work when one of the actions is small. So this equation says, well, this is just pointing out what we already know, that Ji toy is equal to, in the event that the true action, the ith action vanishes, right? Supposing one of the actions vanishes, the orbit you're trying to find, right? Suppose the radial action vanishes. So I'm trying to find circular orbits, or shell orbits. This is a shell orbit. This is an orbit on which the radial action is incredibly small. So then remember Jt in general is equal to J plus this Fourier series. If the J I'm seeking is nothing, then Jt is equal to this Fourier series. But this Fourier series is going to be as often negative as positive, and actions are inherently positive. So it's clear that this Fourier series cannot give me viable values of J. So what does this tell us? This tells us that you can't use a generating function of this sort to find the very skinny orbits, the orbits in which an action vanishes. It must be that the image of the orbit JR equals naught, which is what we call a shell orbit, and here is, well, the black line is a piece of a shell orbit. This actually has to be mapped already onto the toy orbit JR equals naught. And we do that using a point transformation. Now, so in this diagram, the black curve is a circle. So what is this? This is a plot of radius versus z. So this is the meridional plane. And I'm trying to calculate an orbit which is this red orbit. This red orbit is a shell orbit. Well, what really is it? It's an orbit that's strongly inclined to the galactic plane, and it precesses because the galaxy's potential isn't spherically symmetric. And when you work your way through that, you come to the conclusion that you end up with the trace of this orbit in the RZ plane is like this. And that clearly isn't going to map onto this black orbit, which is a similar shell orbit in the spherical isochrone potential. So you have to map this thing into this thing by brute force before you can use this kind of generating function. Now, fortunately, the red thing is very closely approximated can be very closely approximated by an ellipse. So what we need to do is to do a transformation in position space which is what's called a point transformation. The point transformation is a canonical transformation where you map places in real space, coordinate space, to places in coordinate space without messing with the momentum. Right. So that's what I've got to do. I've got to map this into this, and this diagram shows the result of doing that. But we do that using precisely this ellipsoidal coordinate system. So I define so r and theta are the spherical polar coordinate variables that are for which I know the transformation to toy angle action variables. So I've got formulae that turn toy action angle variables into r theta, pr, and p theta. And instead of and from those r and theta, I construct a variable big R and a variable little z by these formulae, where delta is a parameter at my disposal. It's a free parameter. And the name of the game is to arrange that the true angle action variables get mapped by the generating function that we've been discussing to the toys, which then get mapped by the Hamilton-Jacobi equation by the analytic formulae for the isochrone that comes from Hamilton-Jacobi to r and theta, which then get mapped by this point transformation you see here to r and z. It's also important, turns out to be in general quite a tricky aspect. It's not good enough just to do what I did on this slide, to map the black curve onto the red curve. You have to do it in such a way that in momentum space, everything works out well. And this diagram is showing that as it happens with this mapping, it does work out well. So this is a Z, I think it's a Z PZ plane, or it's, sorry.
Yes, PZ.
That is Z, not PZ. Yeah, anyway, yes, I think it's a Z PZ plane. So this is sort of showing what's happening in momentum space, and you can see that there's a red curve and a black curve. There's also another curve down here. And they're all coincident. And in general, well, I won't go into details about exactly how you have to do that. In this case, you kind of luck out. This point transformation sort of just sorts it for you. In general, it turns out to be slightly more complicated. Okay, so now we've now got a complete scheme for forcing for mapping our isochrone toy toruses into toruses, orbital toruses of the galaxy. We've got one more thing to do before we go home and declare victory, and that's we've got to find the frequencies, omega I. So far, what do we know? We know the S's. We know our computer has chosen these numbers S, right? That's what and it chose delta. It chose, sorry, the point transformations. This thing here it chose, and it chose the S's. But before we can say we have complete control of the problem, we need to find the frequencies, and we need to find these derivatives of the S's with respect to the actions. And the way you do this is you write down this rather trivial equation. You say that a frequency is dH by dj. But by the chain rule, dH by dj toy times dj toy by dj true is the same thing. And this is true at any value of the toy thetas. So what you do is you work out what dH by dj toy is. You've already worked that out actually in order to do the energy minimization of the variance. This has already been worked out using the chain rule in terms of dH by ds, ds by dj. This is what we're looking for. This is what we're looking for. This we already know. This we already know. This is right. This you already know, and you can get an equation of this sort at any value of theta t you like. So at all the points on your grid, your grid in toy angle space, you've got an equation like this with unknowns here and unknowns here and coefficients you've already calculated. So this is a linear system of equations. Your computer solves it in a flash and tells you what these gradients are and what these frequencies are. Now you're in complete control. So what can you do with a torus? Well, the simplest, most mindless thing you can do is you can calculate a trajectory. You can just put theta of time is equal to any starting theta you like times omega t, where the omegas we've just solved for, and that will give you a time series. That'll give you a version of the orbit. And the diagram over here shows such a time series in black, by just obtained by integrating Runge-Kutta-wise in a realistic galaxy potential, and it shows you in red the time series you get out of this. So it works. You can ask the question, will the star visit this point here or this point here, right? And if so, at what velocities? Typically, as you can see from here, you visit any point within the orbit, you visit with 4 velocities because you go along each of these lines in one of 2 directions. So you can ask that question and answer it in a flash. You basically solve iteratively for the angle variables. So for each of these points, which lies within the orbit, there will be 4 angle variables, 4 different angle variables at which x comes to that location, and each set of angle variables will correspond to 1 velocity. You can ask, what density does my orbit contribute at any point in where the orbit is visited? Well, what's that? That's the density associated with an orbit of action j at location x. That's the integral d cubed v, integral over velocities, of the distribution function evaluated on this, where the distribution function is of this form. It's a Dirac delta, so it's nothing unless j prime is equal to j. This ought to say d cubed v primed, I guess, because whatever. Yeah. Right. So the distribution function is this, and d cubed v can be written as d cubed j primed times the Jacobian of v with respect to j prime. So obviously the Dirac delta gets rid of the integral, and we conclude that this density is equal to dv by dj. And I hope you will believe me that you can, given what we already know, the s's and the derivative of the s's, we can evaluate this thing. This can be analytically evaluated. And the colors here show what the density is that this orbit contributes in these various points. There's a certain amount of steppedness here and here, but that's nothing to do with the torus mapping machinery. That is to do with the fact that I've only plotted this with a finite on a finite spatial grid. I've not done it very well, I guess. So this is worth noticing that the density is least in the middle, and it rises as you approach the edge. And in fact, it's divergent. As you approach one of these edges, the density contributed by a single orbit diverges like 1 over the square root of how far you are from the edge of the orbit. And that is for galaxy modelers, that's a genuine issue in a practical sort of way. But it all emerges from this formalism very well. What else can you do with your torus? Well, you can construct surfaces of section in a flash. So here's an example. This is an RVR plane. The curve is being drawn from a torus fitted to certain actions, and then the red points are obtained by numerically integrating the orbit from one point using as initial conditions 1 point on the torus, and you can see that the numerically computed consequents do indeed lie on the curve. It's incredibly faster if you want a surface of section. It is very much faster to have the torus and just draw the continuous curve than to integrate the orbit until you're blue in the face and get a lot of red points. what I think is extremely important is you can interpolate between tori, and this diagram down here is to illustrate the point. So what I've done here is compute each of these black curves is obtained is a surface of section just like this, right? So this is a cross section through a torus, right? Can you imagine the donut coming out of the board and going back in the other thing, and you kind of cut it, and that's what you see here. That's what in the RVR plane. Okay, so each of these black curves has been computed by torus mapping, and there's nothing very. I mean, this is just showing going from toruses which have a large radial action to a torus which has a very small radial action. But what's interesting is this red curve. This red curve is obtained by interpolating between this torus on the outside and the smallest torus on the inside. And I think you can see that the red curve almost covers the appropriate black curve. It doesn't quite, because interpolation between such, you wouldn't normally do interpolation between points which lie so far apart. So this is an exercise to kind of demonstrate to stretch the machinery to destruction, I guess is the right way to put it. But the point is that we have got an expression for our torus in terms of the s's, and the ds by dk's, and these objects, there's nothing to stop us just doing linear interpolation in actions of these objects. And this diagram is illustrating that when you do that, you generate the coefficients to quite high precision of a torus that you could have constructed at that location from first principles. So, and this is actually very important. There are practical applications of this which haven't been implemented. For example, to computing streams, stellar streams in the galaxy. But the application that I'm going to talk about considerably is that it allows you to create integrable Hamiltonians. So what you do is you foliate phase space with tori. So you give me a phase space and a Hamiltonian. I will fit toruses to that Hamiltonian on a grid in action space. These toruses will provide will sit inside each other as these toruses sit inside each other. And then I will be able to create as many toruses. I will, through this interpolation log, I can then, in a flash, create a torus for any actions whatsoever in this space, and they all fit together. And then I can define an integrable Hamiltonian as follows. I can say that H0, the integrable Hamiltonian that I'm defining at J, is the mean value at J. It's the mean value of the true Hamiltonian, whatever it is, over the torus of J. So I can construct a torus for any J. I can, in a flash, or not quite a flash, but with not that much work, I can find out what the mean value of H is over there. And then I declare that to be the value of H0 on that torus. And this Hamiltonian is integrable in the sense that by construction, it's constant on toruses. This illustrates, I think, also an interesting point, which is you can see now, I hope, that a given set of toruses, a given foliation of phase space corresponds to an arbitrarily large number of Hamiltonians, because you can assign any number you like. You can assign these Hamiltonian values on toruses any way you like. I'm interested in a particular Hamiltonian of because it's for the galaxy. So I have a narrow-minded view. I want to assign the Hamiltonian value on J by this average value of my real Hamiltonian over the torus, right? But I don't have to. I could imagine other Hamiltonians. So this is right. Okay. And now I can do perturbation theory. So because my original Hamiltonian probably wasn't integrable, it's not actually possible to find a torus such that the Hamiltonian is exactly constant, the given Hamiltonian is exactly constant on toruses. So we have to be braced for the fact that this average value, there will be fluctuations around this average value, right? The real Hamiltonian will have a value on this torus, which is a function of theta. And the difference, but the difference between h of theta and j and h0, the average value with respect to theta, will be small. And so that's what we do perturbation theory on. We treat this as a perturbing Hamiltonian on the integrable Hamiltonian H0, for which I already know the torus is. So the point I think to make is that tori encompass orbits, but they are very much more powerful. You can do much more with a torus than you can with a time series of an orbit. And I think this is something which galaxy modelers aren't yet taking advantage of. Okay, so now something a lot less beautiful. I think torus mapping is very, and I should say that we have an implementation of torus mapping now, which makes this torus construction, even doing a foliation, even constructing a lot of toruses, really only takes moments. Finding a single torus is it's sort of work comparable to integrating an orbit. It's no big deal. Your laptop just does it. Okay, so now there is a snag. Nothing in life is perfect, and this jolly well isn't. The problem is that a lot of the time when doing galaxy modeling, I want to take X and P. I've got a star. I know where that star is in phase space, and I would like to find the angle action coordinates. And torus mapping isn't well suited to that. One could do much better than, one could write algorithms for doing this. It would have to be kind of iterative. We have done in the past ways for doing this, but we haven't got slick code for doing this at the moment. It isn't straightforward. And what people do overwhelmingly is as follows, which is a lot less elegant. And I don't think it's necessarily more labor saving, but I'm not sure about that since I haven't got a slick code for doing this with toruses. So what's done is as follows. So this apparatus is widely used. Torus mapping, I regret to say, is not widely used. It has been used by other people, but not as much as it should be, and that's partly, I think, because of unavailability of good code. I now have very good code. I think that problem should go away soon. Anyway, so if I have a Steckel potential, right? So a Steckel potential is one of these potentials for which you can solve the Hamilton-Jacobi equation. If you use this UV coordinate system that I mentioned earlier, right? This axisymmetric oblate ellipsoidal coordinates. Notice a funny thing. I'm interested in I'm thinking about orbits in an oblate gravitational potential, flattened gravitational potential. But what I need for that job is actually a prolate ellipsoidal coordinate system, right? The foci here lie along the z-axis, not along the r-axis. So that's the way it works. Okay, so a Steckel potential in terms of these coordinates is of this form. It has two free functions, u of u and v of v. And on the bottom, there has to be this weird combination of sine squared u and sine squared v. Right. So supposing my real potential, it could be approximated by this. If that were true, then this sine squared times my real potential would be this difference between two functions of one variable. So my real potential is absolutely a function of two variables. But if it were a Steckel potential, multiplying it by this would unwrap it into the difference between two functions of one variable. So the Steckel fudge amounts to pretending that this really happens. So this is going to be my arbitrarily given potential, and I'm going to fantasize that it can be written as this difference. That being so, now I can't actually find what u of u and what v of v is, but what I can do is compute this thing. I can consider the difference between u of u and u at some fixed point u naught. Why? Because that would be this, right? This allegedly is u of u, sorry, minus v of v, and this is allegedly u of u naught minus v of v. So the v of v's would go away, and we'd be left with u minus u naught. And similarly, I can compute delta v by the same trick, right? I basically subtract from my alleged thing, I subtract the same thing with a different value of one of the coordinates and the same value of the other coordinate. And the approximation that we're making, so this is something that is defined by, in fact, defined by this in real world, it's defined by this equation. It's not really a function of u only. It, in fact, will have v dependence, and the approximation is that it has very weak dependence. This is, if we define delta v to be this, it isn't actually a function of v only. The approximation is that it has very weak u dependence. So that's how we proceed. Now we've said that u of u is equal to u of u naught plus delta u, right? Because we define delta u to be in this difference, and we put this into the expressions. These are expressions that come from Steckel's work, as it were. They tell us what the u momentum is, the momentum conjugate to u, as a function of u, right? Because everything on the right here is u, no v. And they tell us what the momentum conjugate to v is in terms of v. So what we do is we stuff this into here, and then we absorb this constant, which we don't know actually, into I3, and we absorb the corresponding v constant into here, and we get an expression. Sorry, we absorb we get these expressions for constants. So now we have an expression for the u momentum as a function of u and the v momentum as a function of v, and we can conduct these integrals and evaluate our actions. And you can extend this formalism to get the frequencies. Okay, so I call this thing the Steckel fudge because because it's a leap in the dark. It's not a controlled approximation. We're just saying, well, when I integrate orbits in my potential, the orbits look, they have quantitative similarities to orbits in Steckel potentials. So I think it isn't that different from being of the form u of u minus v over v over those sine squared u minus etc. Right? But I've got no expansion parameter. I've got no power series. I've got no, I've got no way of, yeah. What I do have is some adjustable constants. I have the focal distance delta of the coordinate system. I have the numbers u naught and v naught, which are used in the defining of delta u and delta big U and delta big V. It's pretty obvious that v naught should be put equal to pi upon 2, which means it's a v naught is pi upon 2 is a point with z equals naught. And it's also pretty clear that u naught should be the value of u at which the shell orbit, that's the orbit with JR equals naught, cuts the, so here we had the shell orbit. This is the RZ plane, but that can be mapped into the UV plane. And the point for a given angular momentum, the shell orbit cuts this plane at a certain value of R or a certain value of U, and that should be what U naught is. So those two constants are pretty much chosen for you. Delta, you need to consider what you take. What you can do is use this fudge to calculate the angle action coordinates at arbitrary places, and then you can integrate orbits from those places and keep calculating. So I choose a place, I integrate an orbit, and along the orbit, I calculate the angle action coordinates. If everything was good, the angle variables would increase linearly with time, and the actions would stay constant. So if you keep away from resonant orbits, we'll be talking about those later, the dispersion in J, so you'd like J always to get the same value. Actually, you get actions which vary along the orbit, but typically by 2% or at most 5%. So it's for real galactic potentials, it works reasonably well. And Eugene Vasilev in 2018-19 released a library of galaxy modeling software, A Gamma, that implements this fudge incredibly efficiently. So it is a very serviceable tool, and I'll be showing results obtained in this way. As I said, it's a somewhat it is a fudge. It is not a satisfactory approximation, and I think it would be. I'm keen in principle, time, life, everything being available to replace it with torus modeling, which I think is a more rigorous and ultimately satisfactory arrangement. Okay. A lot of people do n-body models, and something you might like to do to understand your n-body model is to determine the actions of your orbits. And something that you can do is as follows. You can, all the way along your orbit, at all the locations upon your orbit, you can, having picked on a point transformation and an isochrone potential, just as we described when doing the torus modeling, you can calculate theta t and jt. You can calculate the toy angle action variables along the orbit. And then you can say the actual action should be the toy action I've just calculated minus blah de blah, and my angle variable, which will be some unknown constant plus an unknown frequency times time, is equal to the toy variable that I've calculated plus these derivatives, which I don't know what they are, times sine k theta toy, which I've calculated. So this sine I will know, this I will know, that I will not know, nothing on the left I will know. I won't know this on the left, but I will know this. I don't know that, but I will know the value of the cosine, right? And then I can, I have these equations, a pair of these equations at every point, theta t, jt along the orbit. So I can have as many of these equations as I want by integrating for a bit longer. And it what does it do? It provides me with a linear system of equations for the unknowns. J is unknown, theta naught's unknown, omega is unknown, sk is unknown, and dsk by dj is unknown. So I have a finite number of unknowns and an unlimited supply of equations. So clearly I can solve the equations probably in some least squares sense, because it's an overdetermined problem, and determine these quantities here and get a model, an analytic model, a torus belonging to the orbit. If your orbit is genuinely quasi-periodic, that's pretty much guaranteed to work well. If the orbit is irregular, it won't. So now let's talk about perturbation theory, which is... Is it a good moment? Yeah, is it a good moment? Yes, it's a good moment. So let's have a break. Okay. Yeah, because this is something different. I'm available for questions during break. Okay. Here we go. Yeah. Okay, so we'll be doing perturbation theory more or less one thing with another from now on. So the name of the game, of course, is that we are given some Hamiltonian, we'll call it H1, and we choose an integral Hamiltonian H0 that's close to it. And this is classically, this is going to have to be chosen to be something like the Kepler potential or the harmonic oscillator. But of course, I'm going to choose for H0 one constructed by torus mapping. And then we say, let's consider a one parameter family of Hamiltonians, H beta being H naught plus beta times H, where H is 1 over beta naught times this, so that when when beta is equal to beta naught, the Hamiltonian becomes h naught. Sorry, when beta is naught, it's h naught, and as beta becomes beta naught, h becomes the real Hamiltonian. No, I've done that wrong. Doesn't matter. You get the idea. I have a one-parameter family of Hamiltonians which start off as the integral Hamiltonian and finish with the Hamiltonian that I'm given. And what we're going to do is look for the generating function when we're dealing with h beta, the generating function that moves us between the angle action coordinates of h naught, which is of course the theta naught and j naught, and the angle action coordinates of h beta, which are j beta and theta beta, wherever that is. And you've seen this before. We get theta beta by taking the derivative. And S, I'm writing as the identity transformation. I've already covered that this is the generating function of the identity transformation plus beta times the small parameter times some other function, little s. And so we have this, so that theta beta is theta naught plus a bit that depends on beta, and this is this, this is this. And the name of the game is, so this diagram is supposed to illustrate, I think, that these full curves are the toruses, cross sections through the toruses of J that are described by J beta. So they're the orbital toruses of H beta, whereas the dotted curves show the toruses of J0 of H0. And what we're trying to do is map the dotted curves into the full curves. So what we do is we write H beta as a function of the theta naughts and the J naughts, that of course, since H beta has been defined to be the sum of H naught and beta times H, that's true. Then we say, but J naught is equal to J beta plus a bit, etc. And then we Taylor series expand this. So this is H naught of J beta plus the H naught by dj, which is omega naught, times this small amount, beta times what's it. And similarly, we can Taylor expand H, but we don't bother to because H is already of order beta. This term is already of order beta. It's already small by hypothesis. So we can evaluate H just on theta naught and J beta like that. And what we want to do is arrange for these two terms to cancel each other so that this thing becomes a function, a known function of H of the actions. So this is just a restatement of the line over the page. What we do is we Fourier expand. This, of course, is a function of an angle variable, so it is inviting us to Fourier expand it in the angle variable. H is a function, similarly, we expand in the angle variable. And these two terms cancel when S is equal to this. And so given that S is equal to this, we can calculate, for example, the unperturbed action as a function of the true action and this over here. So so this tells us that the unperturbed action is equal to the true action, which of course is constant if we solved our problem correctly, plus this Fourier series. So the unperturbed action wanders around a bit as the true action stays constant. And the diagram tells you how that works. As I go around the full curve, I'm now outside of this curve in J0. So my J0 will be rather larger than it was here, where so when I'm here, my value of J0 will be smaller than the value associated with that curve. And when I'm here, it'll be larger than. So this offset is the Fourier series that we have constructed. Right. So now let's talk about resonances. So that's all very straightforward. The problem arises if we have a resonance. So what we have is this resonant denominator k dot omega naught on the bottom. So remember, that is a vector of integers, and this is a vector of frequencies. And it just, by Murphy's law, it's going to happen that for some k, sometimes for some actions, for some k, this on the bottom is going to go to 0. And then disaster, because if h isn't simultaneously 0, if there isn't a perturbing term in the Hamiltonian, if there is a perturbing term in the Hamiltonian associated with this action, then this thing on the bottom vanishing is going to cause this allegedly small adjustment to J0 to blow up, and we have a disaster. Now, let me talk about a really basic example of this. If a star like the Sun, which keeps close to the galactic plane, has a vertical frequency of oscillation above and below the galactic plane, which is significantly bigger than the radial frequency with which it oscillates in and out from the galactic center. But if you go to stars with sufficiently large that move far from the galactic plane, then you will find that omega z becomes less than omega r. You know that that's the case because in a spherical potential, the frequency with which you oscillate vertically is actually the frequency with which you go around and around, and that is always less than the frequency with which you oscillate radially. So there has to be a level of excitation vertically at which omega z is equal to omega r, and we have a dirty great resonance. Now, here I'm showing, I've picked my my actions so that my vertical action, so that this resonance lies in the is right there. So here we have this is the R RPR plane. So each of these red curves has been made by torus mapping, and the area inside one of these red curves, it's easy to show, is 2 pi times the radial action. So here we have a load of red curves with large radial action, and you can see they kind of foliate this piece of phase space rather nicely. In the middle, we have red curves with small areas and therefore small radial actions, and they provide some kind of a foliation. And I think you can see some black points. I hope you can see some black points, which are obtained by numerically integrating the equations of motion. So this is a surface of section, and I think you can see that out here, the black points lie along red curves, and in there, the black points lie along red curves, and everything's wonderful. But you can see that there's a complete conflict because the red curves in this region are rather elongated vertically, whereas these are elongated horizontally, and we have the consequence of which is that they overlap. So here, there are points which lie on toruses constructed for 2 different actions, but that's not possible because what that means is that these points, if my toruses were orbital toruses, then these points would sit on 2 orbits, but each point in phase space can be on exactly 1, no more than 1, well, exactly 1 orbit. So it's clear that some of these toruses constructed by torus mapping are not orbital toruses. So torus mapping, when there's a resonance, generates these conflicting tori either side of the resonance. Another point to notice is that the area inside the last of these ones is manifestly greater than the area inside the last ones of these. So there are actions. Remember, the area is 2 pi times the radial action. There are radial actions for which you cannot, even the torus mapper cannot construct a torus. So what happens if you launch, you take a point in this area, which is not one of these 2 areas, which is not covered by toruses, and take a point there, use the initial conditions to integrate an orbit, and this is what you get. So these blue points have been obtained by integrating a series of orbits with initial conditions in this zone of missing actions. This is a region in which you can find no orbits with appropriate radial action, and you see you get these. It's clear from the numerical integration that there are toruses, orbital toruses in this zone that very beautifully fill the gap of the missing actions, but their structure, their sort of geometry is different from the toruses that we were trying to find with the torus mapper. And this is generic. This is a generic situation when we have a resonance. So that vanishing of this, telling you that this generating function was useless, is signaling not the, I mean, it's signaling that something physically interesting has happened that you're not equipped to deal with. So the question is, how do we deal with that? So that's what resonant perturbation theory is all about. How do we handle this? So we've got some k, some vector, big K, such that k dot omega goes to naught. What does that mean? That means that there is a slow angle. So there is a particular unperturbed torus on which k dot omega equals naught. That means that if we go to nearby toruses, since omega is going to be a function, a continuous function of the actions, k dot omega is going to be small, but not zero. That means that there's going to be an angle, k dot theta, big K dot thetas, which evolves slowly as a low frequency, a frequency which actually goes to zero at this magic place. So what we do is we transform. I think I told you yesterday that we can do canonical transformations between systems of angle action variables, provided we use matrices with integer coefficients to do the transformation. So that's what we're going to do. We're going to transform to angle action variables so that one of the new angles is theta slow. And here's a generating function. So I've chosen the first part of this generating function to be, so this is a function of my existing angle variable and my newfangled actions. And I'm taking my newfangled action, my first term is going to be newfangled action 1 on k dot theta, which is my new slow angle. And then I'm just rather randomly writing down j2 primed theta 2, j3 primed theta 3. Then in order to find in order to find the first primed angle variable, I differentiate this with respect to j primed. And what do I discover? I find that theta 1 primed is equal to this, because the only place that j1 primed occurs is here. So I differentiate it away, and I find that theta 1 primed, which is equal to k dot theta. So that's good. My first newfangled angle is the slow angle. It turns out that the other two angles with this choice, which is totally arbitrary for the rest of the generating function, my other two angle variables stay the same. If you ask what are the new actions, well, j slow is the derivative of this with respect to, so that's j1 primed. It's the derivative of this. Maybe I should have got this one. Yeah. In order to get j1, I have to differentiate this with respect to theta, right? In order to get back my old action, I differentiate this with respect to theta. And what do I get? I get K1. Yeah, I get K1 times J1 primed, and that's what this is, I think, telling me, etc. So I get these, and then I've inverted those equations to get these. So that's my set of transformations. What we want to now is we write my Hamiltonian as a linear combination. I write my Hamiltonian in terms of the newfangled variables. So that means I Fourier expand it. Here's the coefficient in the of as it were, k equals naught. So this is just a Fourier series, a generic Fourier series, and then I can write down Hamilton's equations. I write down Hamilton's equations. Now, what is this? So that's what this is. If I ask what is happening with So here we have all the newfangled angle variables. And what I now argue is that one of these angle variables, theta slow, which is the first of the primed angles, is varying slowly, and I need to take account of that. But I don't need to take account of theta 2 primed and theta 3 primed because they have fast frequencies, and this term is going to change sign before, it's going to change sign quickly before anything much can happen over here, before it can significantly affect cause significant change in one of the new actions. So I drop from these equations, from this sum, I drop the fast oscillating terms, any term here which has a contribution from theta 2 primed or theta 3 primed, I simply cross out on the grounds that it averages to 0 sufficiently fast, and then all I'm left with is a Hamiltonian that says that involves a sum over vectors which are k1 times k1 comma nothing. So I'm insisting that these components of k, I drop terms in this sum where these components of k are not 0 on the grounds that they generate terms that average to 0 very quickly. So I'm left with this, and that means I've reduced the problem to motion in the j slow, theta slow plane. The motion has been reduced to 1 dimensions. If you ask with this Hamiltonian, what is the equation of motion of j2 primed to j3 primed? Well, the answer is 0, because the Hamiltonian no longer depends on theta 2 primed to theta 3 primed. So I've got two constants of the motion, j2 primed to j3 primed, rescued from the wreck of the old system. And where is j2 primed and j3 primed? j2 primed is this linear combination of the old actions, and j3 primed is this linear combination of the old actions. So these things are constant, and the old actions are going to be varying because they involve j1, and j1 is pretty much the slow action, right? So so a couple of the actions are going to be varying, but in a way that we understand, so as to hold this thing constant. And meanwhile, j slow is going to have a non-trivial equation of motion, which is governed by this Hamiltonian. The traditional thing to do now is to Taylor expand h naught. So h naught is a function of the slow action, and we know that the h naught by dj slow evaluated on the resonant orbit is nothing, right? Because that's omega slow, and that goes to nothing on the resonant orbit. So if we expand everything around the resonant orbit, if we say j slow is equal to j resonance plus delta j, then the derivative of h naught with respect, the first term in the Taylor series, the first non-trivial term. When I Taylor series expand this, I will get a constant plus a term plus delta times dh naught by dj plus a half d2h naught by dj squared times j delta squared plus ... I get rid of the constant because who cares about a constant Hamiltonian? It doesn't create any motion. I get rid of the first term because the coefficient of delta in the Taylor series is omega slow on resonance, which vanishes by construction. And so this is my approximation through second order in delta j. This is my approximation to the slow Hamiltonian. It's simply a quadratic in delta j. How far I am from the resonance. And similarly, I Taylor series expand the perturbative driving term, which is multiplied by this Fourier series in k slow. So I Fourier expand that, and in principle, that gives me 3 terms. And then I say I've got motion in a 2-dimensional plane. That motion will be along surface. In that motion, the slow Hamiltonian will be constant. So I can say slow Hamiltonian, which is this. So here are the terms which are proportional to delta j squared. Here's a term proportional to delta j, and here's another term. But this lot is equal to constant, which we'll call energy. And if you now give me a value of theta slow, this equation becomes a quadratic equation for delta j. right? Because this then becomes if you give me theta, a value of theta slow, this becomes a number. This coefficient of delta J becomes a number, and this becomes a number, right? So I've got a quadratic equation. I know how to solve quadratic equations. If there are two real roots to the quadratic for any value of theta slow, it means that the theta slow goes from 0 to 2 pi, but it goes from 0 to pi to 2 pi back to 0, it goes round and round as we have what's called circulation. Well, obviously, if there are two real roots for only a limited range of theta slow, then theta slow goes from, say, 0 to some maximum value, and then without reaching 2 pi, and then it comes back down through 0 and then down to a smallest value, and it just oscillates in a limited range, and that's what's called libration. And these equations reduce to the equation of a pendulum, the exact equations of motion of a pendulum, if the only term we need in this series is k equals 1. So if you out of these sums, if you just take the k equals 1 term, whoops, oh dear. In these sums, you end up with the slow Hamiltonian looks like this. And the equation, the Hamiltonian of a pendulum is this, right? Here's the kinetic energy, and here is the potential energy, which when we do simple harmonic motion, we approximate this cosine by a constant minus a half theta squared. So we have a pendulum Hamiltonian. We get new, so we out of the wreckage of the old system, you recall, we salvaged two constants of the motion, J2 primed and J3 primed, which were combinations, two distinct combinations of the old actions. And now we can get another constant of the motion, which is the slow action. So that is the integral d theta slow times J slow, around and about, which turns out to be simply the integral of d theta slow of the difference in the two roots in the quadratic equation over the range in theta in which the quadratic equation has two roots. So when we get to the ends of this range, these two roots coincide, right? Because the solution to the quadratic equation is, minus b plus or minus the square root of b squared minus 4ac. And when the two roots coincide, that square root vanishes and these two things become equal. So this integral is what we need to do the integral all the way around of theta slow, b slow. And we similarly, this formula tells you what the slow angle is. So this is an example. So what I'm plotting here is a blow up of this space here, or if you like, this space here, right? Except that these magenta curves are computed from this resonant perturbation theory using as unperturbed action angle variables the ones that provided by torus mapping. Torus mapping created this curve, and it created this curve, and then by interpolation between toruses, I've created this curve just for illustrative purposes. But in order to draw these curves, all through this region, I need unperturbed angle action variables, and they're obtained by interpolating between here and here. And I hope you can see some dots. They're pretty hard to see because the dots are a consequence obtained by numerical integration of the full equations of motion, and you can see that they are overlain by the magenta curves obtained by these analytic formulae laid on the angle action variables provided by torus mapping. Okay, so that's just an illustration of that's all about resonant perturbation theory, very widely used apparatus, very traditional apparatus, but giving very accurate results because with the Hamiltonian the unperturbed Hamiltonian obtained by torus mapping, the perturbative term is surprisingly small. Okay, so let's see whether we can do that was for the one-to-one resonance, which inevitably exists for stars in the galactic halo. We don't actually know of a single star, I have to disappointingly tell you, even in this era of Gaia, which is known to be trapped on that resonance. There must be stars there which are trapped on that resonance, but we don't really have a diagnostic at this point. It will be very interesting to know where that resonance lies, because where the resonance lies is controlled by the interplay between the dark halo of the galaxy and the disk of the galaxy. It's the disk of the galaxy which makes the sun's vertical frequency very high, and it's the dark halo of the galaxy which provides the large radial frequency for stars that are on highly inclined orbits. So where that resonance lies is sort of controlled by this crosstalk between the disk and the dark halo, and so you would learn something about the dark halo if you could localize, if you could identify where it is. The thing is, it's not immediately evident, since we only see stars at one instant. We don't, if we could watch their orbits, it would be blindingly obvious. But since we only see them at one instant, it's not so obvious how I'm supposed to tell whether a star is trapped or not. But I suspect it can be done. I haven't done it. I haven't seen somebody else do it. You know, over to you. Let me talk now about, so the thing about, however, that gives you spectacularly accurate results. It's kind of obvious that it will, because the perturbing term, the resonance isn't that fabulously strong, and so the perturbing term is relatively small, so we expect perturbation theory to work very well. Let's be a bit more ambitious, and our galaxy is a barred galaxy. Half of all disk galaxies are barred galaxies. So let's see whether we can construct orbits in the plane of our galaxy, which are influenced by the galactic bar, strongly influenced by the galactic bar, treating those orbits as perturbations on orbits in an axisymmetric potential. All right, that's the game now. Now, the figure of the bar rotates at some rate. So what we want to do is the dynamics in the frame, the rotating frame in which the bar is stationary, assuming that there is such a frame. Now, actually, in detail, it has to be said, it's almost certainly the case that the frame in which the bar is stationary is gradually slowing down. And so this assumption that the bar is steadily rotating is an approximation, which we should bear that in mind when we come in some next cycle on the problem. But this is a sensible first approximation, first idea. So what do? We write down the Lagrangian of in a potential well RZ phi. So previously the potentials have depended on R and Z only, and now I'm including a phi dependence because it's a non-axisymmetric potential, and it's going to be rotating at a pattern speed omega p. And this is the Lagrangian, right? It's obviously radial kinetic energy, vertical kinetic energy, and kinetic energy of going around and around, which is phi dot plus omega p, is the angular velocity, obviously in an inertial frame, which is what gives rise to the energy. And so this is obviously the Lagrangian. You work out what the momenta are, and you find that they're all completely unchanged. PR is PR primed, PZ is PZ primed, and most beautifully, P phi is P phi primed, right? So they don't change at all. And in fact, the only equation of motion that changes is the phi dot equation of motion, when it changes in the trivial way that phi prime dot is equal to phi dot minus omega p. So it's, anyway, that's all very satisfactory and mechanical. And what happens is yeah. Do I need to point this out? I don't think so. Let's keep going. Right, now let's take a very simple bar where we say the phi dependence is just some function of R and Z times cos 2 phi. And for my example, I'm going to assume that the axisymmetric part is going to be this. So it's going to generate me an absolutely flat rotation curve because I'm taking a logarithm of the radius, and I'm going to take the coefficient of this to look like to look like this. It's not really very interesting. It's not very interesting what I'm taking. I'm just doing that. And the thing is that m squared is going to be an ellipsoidal coordinate where q is bigger than 1, and so this is going to be constant on oblate ellipses. So there are going to be 3 really important resonances. The co-rotation resonance, which is where the circular angular velocity of a star is the same as the pattern speed of the bar. So stars are riding round with the rotating bar. There will be the inner Lindblad resonance, where stars are at small radii. They're going around faster than the bar, and the frequency at which they perceive the bar is equal to their radial epicycle frequency kappa. So we expect them to have their radial motion excited because they're being stimulated by the bar's potential at a frequency which matches a frequency which they can respond, namely their frequency of radial oscillation. And the outer Lindblad resonance, which will be where at large radius, where the bar's going around faster than the stars, and again the star perceives the bar because it lags behind the bar in such a way that it perceives the bar at its epicycle frequency, so the frequency which you can oscillate radially. So these are the 3 sort of primary resonances. And when you integrate orbits in your potential, you find something like this. This is the big picture. So at large radius, the orbits are pretty much circles. So these are closed orbits. Sorry, I should have said that. These are sort of backbone of systems closed orbits. So at large radius, you've just got this happening. This dotted circle tells you where the outer Lindblad resonance is. Nothing much very exciting happens to the outer Lindblad resonance. When you get to co-rotation, which is marked by this, you see you have this island. So does that remind you of what we had in the RZ plot previously, right? A sort of an island. So clearly there is trapping at co-rotation. So stars go around these things here. The long axis of the bar, by the way, is in the x direction. So this family of orbits oscillates around a point on the minor axis of the bar. And then this is a blow up of the middle. So the orbits get progressively more elongated as you move inwards from co-rotation, and at some point they become cusped. So they get more and more elongated, and at some point they become cusped, and inside the cusped orbit they start crossing themselves. Meanwhile, another family of orbit appears. So these black orbits are called, they were named by Kontopoulos, the X1 family of orbits, very memorable notation, and these were named the X2 family of orbits, right? We'll see quite what they are. Now, if you plot here angular momentum, J phi, which you define, so angular momentum isn't conserved, but so in other words, P phi, so I shouldn't have called it angular momentum. P phi is your angular momentum. On this closed orbit, because there is a non-axis symmetric gravitational potential, P phi is varying. But having computed these orbits, I know how P phi varies as a function of phi, and I can work out this integral. This integral is going to give me the action, the azimuthal action of these orbits in all rigor, right? So this integral is going to give me a number, J phi, which really is the action, the going around and around action. So that's what's plotted along here. And up here is plotted the value, the numerical value of the Hamiltonian, also called the Jacobian constant dj. And I think you can see, so these red dots belong to these X2 orbits. Then there's a bit of a gap here as you go from the X2 orbits to the next. There's a gap in energy, but not a bit in angular momentum, but mainly there's a gap in energy up to these X1 orbits, the black orbits, and then they continue, and then there's a gap here. These 2 orbits have no angular momentum because they are these orbits. So in some sense, these orbits belong up here, having that amount of angular momentum at the peak and the maximum energy, but they actually have no angular momentum because they sometimes they're going one way and sometimes they're going the other way, and then the X1 family continues. So I hope that gives you some kind of orientation of what the orbits are like in a barred galaxy like our own, the closed orbits. Okay, so what happens when you use perturbation theory? In a rotating frame, you can say that the Hamiltonian is the Hamiltonian in an inertial frame minus omega times p phi. That's just a straightforward result of writing down the relevant Lagrangians. Now what we do is we break this Hamiltonian down into an axisymmetric part, and we bury the non-axisymmetric part over here in the residue. And from here, we can subtract, so we can from minus omega p times j phi. So I've explained how to calculate j phi, and we know what omega p is. So this is all known. H axis is some axisymmetric Hamiltonian. From it, I subtract this, and then all of this is a function of known actions, and everything left over goes into here. So this depends on my unperturbed angle variables, my unperturbed actions. At co-rotation, the resonance vector, remember, at co-rotation, k dot omega now is equal to omega p, and the resonance vector, so this is ordered by radius z and phi. So the slow angle is, in fact, the slow angle is theta phi, the angle variable associated with the azimuthal angle, and that's theta slow. And the conjugate action that changes a lot is j phi. The other two, the two fast actions which are conserved are in fact jr and jz. And if you ask what is the so orbits are going to move on contours, they're going to move in the theta phi j phi plane on contours of this Hamiltonian. And what we see here is an r VR plane showing now the toruses look a bit funny in this space. These full curves are actually pieces of toruses constructed by perturbation theory. So the torus goes round like this, and then it goes back like that. Right? These curves come in pairs, either side of some middle point here, and the dots you can see are obtained by numerically integrating the equations of motion. Over here, you see the orbit so these are non-closed orbits. Previously, I was talking about closed orbits. I'm now talking about orbits which have finite radial action. So here we see in real space, XY space, looking down on the galaxy, we see an orbit on the top trapped at co-rotation. So that's basically an orbit of this family here. So that's a closed orbit of this family. Now we're dealing with a not closed orbit of this family. This black curve is obtained by integrating the equations of motion. And this red curve is obtained by this resonant perturbation theory using torus mapping for the unperturbed Hamiltonian. Of course, this on the bottom could be folded onto the top. I've shown it separate. I mean, there's an orbit like this, and there's an orbit like this, which you can obtain both by torus mapping and by. So I think there are slight differences between the black orbit and the red orbit, but they're very slight. And so the resonant perturbation theory is working well. What about the outer limb lab resonance? So this diagram is quite interesting. What's plotted horizontally is j phi, and vertically is jr. Right? Eccentricity, so eccentric orbits are at the top, small orbits are on the left, large orbits are on the right. Here you see a ladder. Oh, and the coloring here. Sorry, now I've got two versions of this diagram and I can't remember. Forget the coloring. Forget the coloring. It will come to me perhaps which coloring it is. But focus on this ladder. The perfectly resonant orbit runs up this ladder. So this ladder slopes slightly to the left. Can you see that? That's because in order that your going around and around frequency is omega p, as you have more and more eccentricity, you have to move to less angular momentum. And the rungs of this ladder are the curves. They tell you how the resonance drives a star. So I told you that J phi is the slow action. So J phi is being changed when the stars are trapped at co-rotation. Their J phi is changing periodically. So a star is moving along here. It gets as far as there and as far as there. So that's the kind of motion that it does. Oops, sorry. Now consider the outer Lindblad resonance. So along the middle here, you see a straight line. That is the trace of the orbit of the orbit which is perfectly resonant. And now the constants of motion are, so what's constant is J phi minus 2jr, because the k vector is now 1 in the r slot and 2 in the J phi slot. And that means that this is a conserved quantity. So J phi varies and JR varies, but they vary in such a way that this is constant, and that means they move on these lines here, these sloping diagonal lines. Yes, the coloring is actually the Hamiltonian. The white curves are curves of constant Hamiltonian. They're level surfaces of the Hamiltonian, and the coloring is to tell you where the Hamiltonian is low and where it is high. So that the Hamiltonian is largest along co-rotation, and it falls as you go inwards. That's obvious. What's less obvious is that the Hamiltonian decreases as you go outwards from co-rotation. But you can actually see that if you look. Oh, I thought we have seen a diagram where that's relevant. Here. So you can see that your Hamiltonian rises until you get to the orbits trapped at co-rotation, and then it falls. All right. So what we see on the right is in black is orbits. These are toruses made by resonant perturbation theory with dots, which are obtained by integrating the orbits in the full equations of motion. And you can see the dots lie pretty well on the full curves of orbits which are trapped at outer Lindblad resonance. And I guess you can you see the same qualitative features. Well, this does look, the co-rotation case does look different. This is more similar to what we saw here, right? General structure. The blue curves here are showing you the unperturbed angle action variables, well, the unperturbed toruses that are used to do the perturbation theory. So you can see that the perturbed orbit is moving quite substantially. It's moving over many blue curves. The resonant Hamiltonian is shifting the unperturbed actions by quite a lot for the outer of these things. And then you can see here so these orbits are librating because the angle variable in question is sort of measured from the origin here, and it as we go up here, it rises and it reaches a peak, and then it falls and it goes negative. It reaches a largest negative value, and then it rises again because it's an angle from somewhere there. And the quadratic equation is saying that if I choose a particular value of theta, then my ray crosses at one route here and another route there. Now, we also see here a curve which circulates. So this is one of the smallest actions that circulates. And you can see now that my angle with respect to the origin starts at 0, rises, gets to pi by 2 here, gets to pi here, minus 3 pi by 2 and back to 2 pi. So that one's circulating, these ones are librating, and we have a transition between the two. Now this diagram is to raise an issue which is best understood by thinking by why this complication arises by thinking about this diagram here. If I would continue this black line further down, you can imagine that these rungs of the ladder would slope. This one slopes all the way down to almost all the way down to 0. The next one, were I to have drawn it, would have sloped to below 0. That's JR less than 0. But actions are inherently positive. So it can't be that this pattern continues all the way down, all the way down. And what happens is this, that as you drop the JR associated with the torus, the torus you're trying to construct, the effective Hamiltonian, the slow Hamiltonian, which over here looked like this, morphs into this picture. This picture, the blue curves here, are contours of effective Hamiltonian at a small value of JR. What we have here is a hill. Orbits go around the hill, and this orbit is clearly not trapped because it's like going around here, right? So its slow angle is circulating from nothing to 2 pi. No, I'm not sure that's true actually. Yeah, no, we need to talk about the coordinates I plotted this in. So I plotted this in this x px place. I've done a canonical transformation to x is equal to xi cos theta slow, px is equal to xi sine theta slow, where xi is the square root of j slow, right? That's how and then I plotted the slow Hamiltonian, contours of the slow Hamiltonian in this. And there are two sorts of contours here. There are ones which go all the way around, they go from negative x to positive x and back again. And there are ones which only go around at negative values of x. And these ones are librating, and these ones are circulating, but there's no discontinuous transformation. In this case, there's a discontinuous transformation. There is an orbit not plotted that goes right in here and then comes right back again. And then inside here, there are ones that circulate. Outside here, there are ones that circulate. In this case, the transformation is continuous, and you can't describe this behavior with a pendulum equation. How are we doing time-wise? It's time to stop. So I think we'll leave it at that. I think I've said what's necessary, and we'll maybe have a little bit to say about chaos at the beginning tomorrow before moving on to other things.
Thank you.
If you have questions, do come and talk to me offline.